Welcome back to our course on advanced hydraulics. We are in the second module on uniform flows. So, last few classes we are dealing with the various topics related to uniform flow. In the last class, we discussed on the procedures to compute uniform flow. We also discussed on the concept of hydraulic exponent for uniform flow. Also, we suggested how to compute uniform flow in channel sections with composite roughness, that is how to evaluate the equivalent coefficient of roughness for various situations. So, today we will be going with the following topic. We will be dealing with uniform flow, how to understand the uniform flow in compound section, and to introduce the concept of normal slope. So, what is meant by channel having compound sections? So, can any one of you tell what is meant by channel having compound sections? A compound section is one, you can see that a compound section, we generally call a section as compound if it has more than one regular area. If it has more than one regular cross sectional area, then along the channel cross section, if the channel and flow properties are varying, then also we call them as a compound channel cross section, that is flow properties varying along the cross sectional area. If these two conditions appear mainly, you usually call them as compound channel sections. So, it is quite difficult to compute flow in compound channel sections, and if you imagine how to compute how to approximate uniform flow for channel compound sections and all, it is quite tedious compared to the normal regular sections whichever you have dealt earlier. Well, if you want to see some examples or some types of compound sections, for example, here I am just drawing a very simple compound section. Now, just to make you understand what is meant by compound section, as mentioned in the definition of the compound section, it is this particular channel is having more than one regular cross sectional area. So, if you see here, it has, see, if you just demarcate these portions, this you can consider as area number 1, this you can consider as area number 2, this you can consider as area number 3. You can now easily see 3 rectangular cross sections in this compound section already given to you. Like that, if many cross sectional areas appear in a channel cross section, many types of cross sectional area appear in a single section, that such type of channels are called compound sections or compound channels. So, a very simple situation is that you can individually compute flow in each of the areas it has been mentioned, and like that finally add it up. That is quite a possibility, but to approximate the entire thing with an uniform flow for the entire section, that it requires certain theoretical concept as well as certain approximations. So, let us see that. Some figurative examples of compound cross section. Now, here say See, this is a channel cross section having a trapezoidal main portion channel and rectangular, or you can say parallelepiped cross sectional floodplain channels or side channels. So, this is a compound section. Another example you can imagine of cross section is that so this is having a triangular cross section as the main channel and rectangular portion as the side channels. So, why do we deal with, why do you want compound sections to analyze open channel flows and why it is required? In nature, most streams are compound in nature. So, how the channels of or the river cross sections may be, say it may be of the following type. Some of the river cross sections may be like this. Now, you see this is a compound cross section. It is having some side portion and some main portion, which the bulk volume of water is being carried in the channel in the main portion. Side portion is also having certain discharges, or you may also see channels where multiple main channels or you can say body channels are there. For example, in this particular type of cross section, say there can be cross sections of such nature, cross sections of river bed in the following form. So, these are typically witnessed in meandering rivers and all. For example, if you go through the Brahmaputra basin, Brahmaputra river system and all, if anyone takes the bathymetric survey or bathymetric study of this bed using hydrographic survey and all, one may witness such type of cross sections where more than one main carrying channel will be present, then some side channels may be present and all. It may be quite possible. So, to analyze the flow mechanisms or to approximate uniform flow in such situations, such type of compound sections, we require, as I mentioned earlier, certain knowledge. Just we will see how we can approximate. How can we approximate uniform flows? How can we approximate uniform flows in compound cross sections? Can you guess? One method of analysis is in the compound section. In the compound section, you have many areas of flow. They may have different properties. Each area may have different properties. Okay? So, you have to devise the strategy accordingly. So, for uniform flow computations, what we do is that for uniform flow computations, the entire compound cross section of the channel is now subdivided. The entire area is subdivided into small areas, say maybe n areas, I is equal to 1, 2, 3, 4 etcetera up to n. areas. Manning's equation is now individually applied to each section, each subsection. Then we suggest that the total discharge in the compound section is equal to sum of discharges from each subsection. Okay. So, whatever I have written it here, if you want to just figuratively show that, say a very small figure I will just draw on the sides here. You can have say such a compound cross section. It is now divided into small areas, say 1, 2, 3, like that n small areas it is being divided. Then Manning's equation is then applied to each of these small sections individually. You can compute the total discharge in the entire section, compound section, the entire compound section, the total discharge in the entire compound section can be obtained as summation of discharges from each of these small sections. Like that one can devise the strategy. So, for demonstration, as we mentioned earlier, let us subdivide the area into n cross sections, that is the entire area, cross section, entire area of the cross section divided into n sub areas. So, the channel sections, say here, if we take the bigger figure here or here, if you see here, as we divide into smaller areas, the entire compound section, if we divide into smaller areas, now here in this particular portion the depth of the channel is shallow, here it is very deep, again here it is shallow. So, various flow properties are coming, as you know that depth of flow is also a property. So, various properties are coming into picture. So, definitely the flow characteristics changes in each of these sections. So, you need to compute velocity in each of the channels. As you see, the depth of flow is different in different channel sections, different parts of this compound section. Definitely the velocity in these portions also will be different. So, you need to compute velocity independently using Manning's equation. So, for that case, again if we suggest that if you compute the quantity independently, if I take this channel independently, this channel independently, this channel independently, if I compute the velocity using Manning's equation and all. So, now you will be having several one dimensional model, fine. So, if that several one dimensional models, if you try to club and all, what happens is that you may have to take into account how much amount of mass and momentum, mass flux as well as momentum flux, how much amount of them they are getting transferred in between the sections, say adjacent sections. If some mass from this section gets transferred to this section, from this section to this section, like that if it gets transferred, you need to take into account all those quantities also. Or if one decides to think in a multidimensional way and try to analyze in a multidimensional way, then also the problem gets complex. So, you need further approximations and further knowledge of whatever way we can do the uniform flow approximations. So, let us see that. So, my question is, flow in open channels. Flow in open channels, we have the top surface of water it is a level surface. You will not see some fluctuated surface and all. Usually, the top surface of water is a level surface, that is pressure is same along the surface of water. So, if pressure is same along the surface of water, the level of the water surface becomes constant, or means level, it will be a uniform for uniform flow. You know that usually the depth of the flow is considered uniform, and the water surface, the top surface of the water, they will also be in a uniform way. So, the pressure along the surface of water, that is also a same quantity here. When you compute total head or energy head, you know that it has components of pressure head, velocity head and datum head. So, your total head is having the following 3 components, that these things we are dealing it from our earlier classes onwards itself. So, along the channel cross section, along the channel main compound cross section, you have different subsections now, and we also suggested that the velocity in each of the subsection may be different. So, that means although the pressure is same along the surface of water, datum head is also same, means for the same thing we are taking the same datum, then the velocity head or the component of velocity, the velocity as it is changing along the portions of the section, not along the section we are talking about, along in the same section along the various sub portions of that particular section, velocity is changing. It creates different energy head along the different parts of the section. So, this is quite abnormal. If there is a different, means along the flood plains of the channel, for example, again let me refer that figure. Say here in this portion you are having a certain energy line or total energy head. Here you are having a different energy head, here you are having a different energy head. Although the water surface at this location, they are same and pressure head is same. So, pressure head is same, water datum is same, but energy velocity head is different in all the 3 portions. So, that creates different energy levels along the different sections. So, you need to incorporate some correction factors or some coefficients in the velocity, which we had already studied. We have already studied the energy correction energy coefficient factor for the velocity, momentum correction factor or momentum coefficient for the velocity. So, you need to take into account those factors also when you compute uniform channel or when you try to approximate uniform flow for the compound channel sections. So, if the n areas are, okay, I will just again one, 2, 3, 4 as in the figure, but generally you can divide the entire cross section into n sub areas, delta A1, delta A2, delta A3, delta AI, similarly up to n sub areas if we can divide them. Then the velocity of flow in each of these sub areas, it can be given as say V1 bar, V2 bar, V3 bar, Vi bar, Vn bar. I hope you why we put the bar here. We are generally using the bar notation, suggesting that you are averaging the velocity for the entire cross section. You know, along the cross section the velocity has further variations, and we gave you how to average the velocities and all. Now, when the compound cross section, for each of these channel sections you are having the average velocity for that particular section. For area del A1 you are having the velocity V1, for del A2 you are having the average velocity V2, for del A3 you are having V3. Similarly, you have different velocity components. So, as we mentioned earlier, you need to incorporate velocity correction factors appropriately. For example, if you are computing the total energy head or wherever the velocity head is coming into picture, you need to incorporate energy correction coefficient for velocity. If you recall the simple, we have given it alpha. If momentum fluxes are coming into picture, subsequently you need to incorporate momentum correction coefficient. If you recall them, we had given it as symbolically as beta. Then how do you compute? Means I hope there is no need to tell you how to compute alpha and beta and all. Anyhow, we will be coming in our subsequent portion of this lecture also. So, discharge in any sub area, say Qi, this is nothing but Vi into del Ai, right. So, if you are applying the Manning's equation, you had already studied conveyance factor for uniform flow. So, therefore, for the ith section, you can have the conveyance factor as K I. You can represent your discharge Q I is equal to K I into S naught of the ith section, that is the bed slope of the ith section, its square root. So, if you obtain it like this, now you know V I bar, this is equal to Q I by del A I, right. So, this is nothing but K I S naught to the power of I to the power of half divided by del A I. That means, V 1 bar is equal to K 1 by del A 1 S naught of the first section to the power of half, V 2 bar is equal to K 2 by del A 2 S naught of the section 2 to the power of half, like that for the nth last section, it is k n by a n s naught to the power of half. So, how will you compute uniform flow velocity now? So, you have now the uniform flow velocity in each of the sub areas, that is you are having the uniform flow velocities in uniform flow velocities in sub areas, you are having them. So, based on that, how will you compute the uniform flow for the entire compound channel cross section? So, this you can do the velocity averaging, you have already studied that. So, let me suggest this as V m bar, that is the uniform flow with average uniform flow velocity for the entire channel section. This is summation of V I del A I okay. So, you have the method to compute the average velocity or the uniform flow velocity for the entire compound section. So, what is this quantity now? You already have the expression for V I bar. So, you substitute that. So, V m bar is equal to K I by del A I S naught right section by half into del A I divided by summation of the individual areas, that will give you the total area A. I is equal to 1 to n K I So, through this way one can compute the uniform flow for the entire, means uniform flow velocity. Please note that one can compute the uniform flow velocity for the entire compound channel cross section. So, as we mentioned earlier, one need to incorporate energy and momentum correction factors when you do such averaging. When you do such averaging, you need to incorporate energy and momentum correction factors. So, how do you incorporate them? So, do you recall that your energy correction factor for the velocity, it was given as V cube dA by V cube A. Your momentum velocity coefficient, momentum velocity coefficient was given as V squared dA by V squared A. So, use the same relationship, use similar relation for compound section. Now, what happens for compound section? There may be a chance that for each of the subsections, there may be, you may be having individual energy correction coefficients, say alpha I. Each subsections, it may be present Similarly, beta I for each of the subsections it may be present. For example, in the earlier figure drawn or say here. Say for such an example of compound cross section, these portions may be flood plane, this may be the side channels and this is the main channel. So, you can suggest like this. This is the main channel, this can be your flood plane, this can be your side channel. Like this you can distinguish or you can just suggest you can the entire compound section can be now subdivided and you can describe some of the properties that this is a flood plane portion of the channel, this is the side channel, this is the main channel or the main body of the channel, like that. If you are able to suggest, now for each, for example, there may be some correction coefficient for the main channel here, there may be some coefficient correct moment energy correction coefficient for the sub channel, for the flood plane channel. They may be quite different also, there are definite chances, because for example, the flood plane normally it is in a dry situation and when the flood arrives it gets wet. So, the roughness of the location may be quite high and this may lead to a different type of energy correction coefficient. In the side channels, the water may be existing, but during flood it may be in a different way, and the main body it is always mostly it is carrying the water, its energy correction coefficient may be quite different. So, you can have individual energy correction coefficient for each of the sub areas. So, you need to take into account that portion also when you obtain average velocity. So, when you obtain average uniform velocity for entire compound section, you need to take into account energy and momentum corrections. You know that momentum fluxes, mass fluxes, all these occur between the sub areas. So, that those corrections you require. If you substitute, when you try to compute, for example, if you try to compute mass flux along between these two sections, if you try to compute the mass flux and if you see that and if you incorporate as some portion of the main velocity along this section, some portion of this is, you need to incorporate the corresponding correction coefficient. You cannot take the entire velocity. Similarly, momentum, if it is getting transferred from this section, from this area to this area, you need to take into account the appropriate correction factors. Similarly, in the stretch of the channel also you need to take into account the corresponding correction factors. So, I can now suggest the energy correction factor is of the following form: alpha equal to 1 to n alpha I V I Q del A I Okay. This is the equation, you just expand it, substitute V I, individual V I, and also you can tell the summation of the sub areas as the total area A, like that you can represent it. I can write the following form now. Alpha I K I Q by del A I whole square S naught of the ith cross section divided by K I Q S naught of the ith cross section whole raised to 3 by 2 by capital A square. You can, if possible, rearrange the terms if you require, you can rearrange them, or you just note it in that way. So, for example, in computing velocity head using the average velocity of the compound section, average uniform velocity of the compound section. If you want to compute velocity head, this is given as alpha m into V m squared by 2 g. So, it is not simply V m squared by 2 g, it is alpha m times V m squared by 2 g. Similarly, the momentum correction factors you can give this as beta is equal to sigma, beta is equal to sigma I equal to 1 to n beta I V I squared into del A I divided by V m squared A. This is the form. So, you substitute V I is equal to K I by del A I S naught to the power of half. You substitute this thing here, you will get the following relation now. I is equal to 1 to n beta I K I squared by del A I S naught of the ith cross section, it is 2 by raised to 2 by 2. So, that is 1 divided by K I squared S naught of the ith cross section divided by the capital total area A. So, this relation also you can keep it in mind. Now, if we suggest that the bed slope is same for all the sub areas, then S naught 1 is same as S naught 2 for all the n sub areas, the bed slope will be same. In that situation, you can write your energy correction coefficient as sigma I is equal to 1 to n alpha I k I cube by del A I whole squared by sigma I is equal to 1 to n k I cube by capital A square. Similarly, the momentum correction factor also you can write it 1 to n beta I k I square by del A I by to n k I squared by capital A. Okay. So, like this you can obtain your energy and momentum correction factors for the entire compound section, and you can subsequently incorporate them while computing the velocity head, momentum fluxes, whatever fluxes or whatever relations you want to use in those things, you need to appropriately incorporate them. So, as we mentioned, the discharge along any of the subsection using your Manning's equation, it was given as k I s naught to the power of half. So, that means your bed slope the root of your bed slope of any ith section, this is equal to q I by k I. Okay. So, if your S naught I is same for all the subsections, that is as mentioned earlier, S naught 1 is equal to S naught 2 is equal to all the n subsections of the cross section of the compound channel, then you can devise a strategy that your q 1 by k 1, this is also equal to q 2 by k 2, this is q 3 by k 3. Similarly, it becomes a property, this ratio, that is q 1 by k 1, q 2 by k 2, q 3 by k 3, they all become a property. And it is, we can consider that this property is some constant c, as this is a constant value or some value, let us approximate, let us give it as capital C. So, as you know that C is S naught to the power of half. So, I can now write q I is equal to k I S naught to the power of half or k I C. Your total discharge Q, this is equal to Q I. Okay? That is, it is equal to k I times C, or your this constant C can now be suggested as q I by k I, or you can suggest that the bed slope S naught is nothing but summation of discharges whole square, and this is equal to q squared by k I whole square, right. So, this way you will be able to get the bed slope of the channel. You will be able to get the bed slope of the channel directly for the compound section. You just need the channel properties. If you have the conveyance factor for each of the subsections, based on that you are able to compute the bed slope also. You can see that as an homework. You can just think of doing the following problem. Homework, you can see, say a natural stream having a main section and floodplain section. Two section is there in a natural stream. The areas, you can give the following data. You can give the following data, area in meter squared for each of them. Say if the main section is having 500 meter square, the floodplain is having 535 meter square. If you observe the wetted perimeter, say it is having 70 here, 125 here. If the Manning's coefficient is given, say here it is 0.035, 0.040, okay, and alpha for the main section, it is given as 1.10, beta for the main section, it is given as 1.04. Similarly, alpha for the flood plane, it is given as 1.11, beta for the flood plane is given as 1.04. You compute the alpha m and beta m coefficients for such a cross section, compound cross section. Okay, you compute them as a homework. So, I will just give you the hint how to start it. You know that for main section, del A1 is given as 500 meter square, wetted perimeter is given as 70. Therefore, your hydraulic radius r, this is given as del A1 by P1 is equal to 7.14 meter. I just computed it for you, you can do it on your own. I am just rubbing it, you can compute it. N1 is equal to given. Subsequently, you can compute the conveyance factor for the main section K1. This is nothing but 1 by n del A1 R1 to the power of 2 by 3. Similarly, for the subsections also, for the flood plane, del A2, P2, R2, N2, K2, you compute them or give them, substitute them in the expression for alpha m, you will get them, substitute them in the expression for beta m, you will get the corresponding coefficient. So, let us start, let us introduce you the concept of normal slope. So, what is meant by normal slope? As we have already mentioned, for uniform flow you have the quantity called, or you have the depth of flow named as normal depth. Similarly, for the uniform flow in the channel, for the uniform flow in the channel, the slope of the bed of the channel is given as normal slope. So, the slope of the bed of the channel in uniform flow, it is called as normal slope. It is defined like that. It is quite useful. One can easily compute. Suppose if the discharge in the channel is given, if the normal depth of the channel if it is given, if the channel cross sectional details are given, and if Manning's roughness coefficient, if this is also provided to you, one can easily compute the bed slope. How do you compute that? You see, q is equal to 1 by n a r to the power of 2 by 3 s naught to the power of half for uniform flow. So, if the depth of the channel is given means, and the cross sectional details if they are given, then these quantities a and r is available to you. So, s naught is equal to q n by a r to the power of 2 by 3, this whole quantity raised to 2. This is the way to compute normal slope. So, why this normal slope is discussed is that normal slope is available only for uniform flow. If you vary the slope of the channel for the same depth, whichever depth of flow, whichever normal depth you have been initially using for the uniform flow, for the same depth, if you just vary the bed slope, you may see that at a certain situation the flow will just become critical. Okay. So, that variations and all one can see in laboratory. You can just do the experiment, you can check it, you can just change the bed slope and see for the same depth of flow, the flow becomes critical or it will changes its course, this thing from critical, subcritical or supercritical and all, it may change. So, that way one can compute the things here. Just see an example here. If you have a trapezoidal channel, its bottom width is given as 6 meters, side slope is given 2:1. So, that is according to our notations and all, small b is equal to 2. Manning's n if it is given as 0.025. If the normal depth of flow is 1.5 meter and it is having a discharge q is equal to 12 meter cube per second. If such a data is given, compute normal slope. So, how will you do that? How will you compute the normal slope? Your solution is, you know, B 0 is equal to 6, all the quantities are given to you. A is equal to y n times B 0 plus small b into y n. Substitute the quantities appropriately. I am getting this as 13.5 meter square. Your hydraulic radius is equal to A by P. I am getting this quantity as 1.062 meter. You just substitute it. Therefore, your bed slope S 0 is equal to q n by A r to the power of 2 by 3 whole square. substitute the quantities whichever are available, that is 12 into 0.025 by 13.5 into 1.062 to the power of 2 by 3, all the whole quantity squared. So, you will get this S naught as 0.0049. So, this is your normal slope. You can also see that at the same slope, if you want to have critical flow for the same bed slope, if you want to have the critical slope, you can compute the corresponding depth of flow that makes the flow as critical flow for the same discharge. That is also quite possible. You have seen how to compute critical flow and all. You can just evaluate those things. So, let me conclude today's lecture. We will just have a brief quiz related to today's lecture. The first question is, in a compound cross section having n sub areas, determine the expression for bed slope. Just few minutes before we have done that. So, you just determine that expression, you just give the expression for the bed slope. Your second question, determine normal slope for a rectangular cross sectional channel. The width of the cross section is 4 meters, discharge in the channel is 10 meter cube per second, Manning's coefficient is given as 0.030 and the normal depth of flow is 1.5 meter. So, for a rectangular cross section channel, it is quite easy, you just determine it. It hardly takes 30 seconds for you to solve them. So, the third question is, what is hydraulic exponent for uniform flow? What is hydraulic exponent for uniform flow? Give the expression for hydraulic exponent. Okay. So, today we will have just these 3 questions. Fourth, let us. So, I hope you have solved these things. The solutions for this thing, I can just give it in the sides. The you have already seen S naught to the power of half for a compound cross section. It is, or you can avoid this half, S naught is equal to q squared by sigma I is equal to 1 to n k I whole square. This thing we have already derived it. The solution for the second question, it is given as S naught is equal to q n by a r to the power of 2 by 3 whole square. On evaluating the quantities, I get the thing as 0.030. So, please verify it. If there is any wrong, please let me know that. So, what is the hydraulic exponent for uniform flow? So, you recall the expression for conveyance factors, k squared is equal to some coefficient c into normal depth times raised to an exponent capital N. So, this capital N is called hydraulic exponent for uniform flow. The expression for capital N, it was also derived in the class. It was given as twice y n by 3 a phi t minus 2 r dp by dy n. Okay. Thank you then. So, we will continue with the same module in the next lecture as well.